Permutations with some identical items. Problem: how many ways can you arrange the letters in the word factor? On the word factor, we have 6 letters. And you'll notice that they're all unique letters. None is like the other. So we can think of this as how many different orders there are of people or items that are unique. And it's simply 6 factorial, or 720. And so you can see the solution below. Okay, now let's look at a word like dole. D-O-L-E. How many different permutations or arrangements are there of the letters in the word dole? So here we have the 24 different combinations or orders, and that's 4 factorial right there, which is 24. Now what about if we looked at a word where there was some commonalities in the letters? So for example, the word doll has 2 L's in it. So the trick here is if we look at all of these permutations, the word doll would actually show up twice. And that would be, if we picture this as L1 and L2, then it would have come up again when we had L2 and L1 in that order. And you'll notice that for every time that you come up with any word like ODLL, that you will find that same order somewhere else. So here we actually end up with 12, or you can think of that as 24 divided by 2. Okay, next, what about the word lol? L-O-L-L. Again, we'll notice that when you look at these permutations that there is going to be situations where we're counting the same word twice. So the word L-O-L-L, where this is L1, L2, and L3, you'll also find it right here with L1, and let's call this L3 and L2. And you would also find it if this was L2 and L1 and 3, and if this was L2 and L3 and L1, or if this was wrong spot there. Or if we're looking at there it is. L2, L1. Oh, we already have that. So L3, L1, L2. There must be another one. There it is. L3, L2, L1. And that would be all the arrangements. So you'll notice the same word was counted 1, 2, 3, 4, 5, 6 times. And so if you read through here and count it out, your total number will be 4, which is 24 divided by 6. Maybe that raises some interesting items to you. So you're left with some questions as to why that might be, and if there's a quicker way to do this besides listing out all these solutions. Well, you might notice that 6, and then here we looked at L1, L2, and L3, and you'll notice that it came up with 6 different ways you could write that. And that's equal to 3 factorial, because that's the number of ways you can order 3 items. And here we had 2 L's, and that's equal to 2 factorial. All right, so we're going to work with some of these ideas here. I'm going to make a bit of a conclusion with you. So right here, because there's 4 factorial ways of ordering it, and because there are 3 L's, then there are 3 factorial ways we need to divide by, because we'd be double counting. On this top situation here, we'd have 4 factorial ways of ordering the letters in doll, and there are 2 L's, so we divide by 2 factorial. And with the word dole, we didn't have to worry about that. So let's look at a different situation. I'm hanging up laundry on my clothesline with 5 pairs of blue jeans, 2 white shirts, 3 black sweaters. How many different patterns can I make? On total, I have 5 plus 2 plus 3, and we're assuming that the 2 white shirts look the same, and the 3 black sweaters look the same, and 5 pairs of blue jeans look the same. So in total, we have 10 items. Okay, so that would be 10 factorial. But the problem is, if I put gene number 1 and then gene number 2 and then follow it up with the rest of them, we would be looking at a different order if it was gene number 2 first and then gene number 1. So we need to divide by 5 factorial to account for the genes. And then we also divide by 2 factorial to account for the white shirts. And then we divide by 3 factorial to account for the black sweaters. Okay? The general way that we figure this out in the formula is n factorial over a factorial, b factorial, c factorial, and we keep going, where each of these are items that are not unique. Okay. All right, let's keep going here. So a little bit of an activity here that we do in class, but we're online, so we'll do it this way. Complete the following questions as a group. Record your own answers. So why are there fewer permutations if some of the items are identical? I think we answered that above, but let's just kind of think through that. Maybe you want to try and write it down for yourself and think before you hear my answer. Okay, so the reason really is that if you have, let's go with two items that are the same, two identical items don't look different when they switch places. Okay, so if you put item 1, then item 2, and they look exactly the same, it doesn't look any different if you do item 2 than item 1. 2a, explain why the formula for the number of permutations with some identical items are identical has a denominator of a factorial, b factorial, c factorial instead of a times b times c. Again, try and think through these before you hear my answer. Well, let's just think about one of them, a factorial. So if you have 3 shirts that are identical, then there are 3 factorial ways of ordering them. Right? So then we need to take it as 3 factorial, not just 3 period, because there are 3 factorial, which is 6 ways of ordering them. B, will there ever be cases where this denominator is larger than the numerator? Explain. Well, what I might not have done a great job of identifying here, and this is consistent with all of our stuff, n is our sample size, right? So really what we're asking in B is, can the number of items that are not unique, can it ever be greater than the sample size? Well, the answer is obviously no. It cannot be. It cannot be bigger than the sample size. And C, use the formula to calculate the number of permutations for A. How many A's are there? 1, 2, 3, 4, 5, 6, 7, 8, 9. There are 9 A's there, okay? So there are 9 factorial ways of ordering them. Then we say on the bottom, well, how many different ways are there of writing those? How many A's are there? And non-unique ways are there of ordering them? Well, there's 9 of them, so we divide by 9 factorial. If you have something over itself, you have 1. And that makes sense, because if you look at the A's there, there's no unique orders that you could put them in. If you switch A's, it still always just looks the same. All right, calculate the number of permutations for the following letters of the word mathematics. Okay, there's 2 ways we can look at this. For the sake of this question, let's assume that these 2 M's are the same. Okay, I see that one of them's capital and one's lowercase, but let's just assume they're the same. So how many letters are there in the word mathematics? There are 11 letters. And then we divide by the number of non-unique items. So there are 2 M's. Okay, there are 2 A's. And there are 2 T's. And that's it. So the answer is 11 factorial over 2 factorial, 2 factorial, 2 factorial. Bookkeeper. Again, we look at how many letters are there in the word. So there are 10 letters in bookkeeper. There is only 1 B, but there are 2 O's. Okay. There are 2 K's. And there are 3 E's. And there we have a number of orders for the letters in the word bookkeeper. Permutation. Okay, this one's a big one. So how many letters are there? There's 15 letters in permutation. There are 4 E's. There are 3 N's. There are, what else do we have? We only have 1 T. We have 1 A. We have the 2 N's already. 1 G, 1 U, 1 I, 1 S, 1 H. There are 4 E's, and that's it. We've got it all. Permutation. And then lastly, we have, what if you had 12 notebooks and there was 6 green, 4 white, and 2 purple? And there's no difference between these 6 green or 4 white or 2 purple. Again, there's total 12 notebooks. There are 6 green, there are 4 white, and there are 2 purple. And there we go. Done. So you'll notice that these are pretty quick questions. Okay, I just love looking at some of this. So some of you may have done this in a newspaper before where you had to unscramble letters to figure out a word. So for example, this first one here is baby. Okay, but what I find amazing is how God's created our brains and how we can solve questions like this relatively quickly, because you got to think through it. What did your brain actually do when it looked at the letters A, Y, B, B? So it saw 4 letters, and it had to unscramble 4 factorial times. There were 2 B's, so it could handle that a little bit by dividing it by 2 factorial. What it was looking at was 24 divided by 2 factorial, which is 2, which gives us a total of 12 different ways that that word could have been written. But you may have found that you were pretty quick at solving that, and your brain unscrambled that. So what about this next one? PICL. So again, we have 4 factorial ways, and they're all unique letters. So there's 24 ways of arranging that. How many ways can it be scrambled? Again, you might find yourself seeing the answer right away. You might not. The word is clip. But it's an amazing thing if your brain actually solves that quick. Again, the last one, ACEF. That's 4 unique letters. So again, there's 24 ways of arranging that. You might notice that the word is face. All right, the last part here is, if you're interested in it, you can take the letters in the circles here. Okay, and you got to unscramble that. So that's the letters B, Y, C, L, I, C, E, and there's 1, 2, 3, 4, 5, 6, 7 factorial ways of arranging those letters, divided by the non-uniques. So there are 2 C's in there. So that's a number of ways you could order those letters, and that's quite the number actually. And if you happen to see it, you might have saw that the word was bicycle.